So what we've done is invited panelists, 6 panelists, to address specific areas in robotics. We have Phil Mooney from Quantum Signal, who's going to talk about sensors. We've got Jeremy Gray from U.S. Army TARDEC, and Jeremy's going to talk about the platform issues. We've got Rich Fredrickson, who's from SOAR Technology, and he's going to talk about intelligence for autonomy. We've got Pradeep, and Pradeep is from the University of Michigan. He's one of the team members of EDS from Magic, and Pradeep is going to talk about perception. And Mark Salamango from 6 Zulu. Mark is going to talk about communications, software, integration, and the like. And Dan Bartz, who's from Booz Allen Hamilton and works at US TARDEC, he's going to talk about user interfaces. So these are all various aspects of robotics and what it takes to build a robotic platform. So we're going to, the objectives of this particular panel are: one, I would like each of you to talk about what you see as exciting in robotics as you do your work. 2, what are some of the technical issues that you find exciting in each one of these disciplines? And then just wrap up with where you see it going in the future. For those of you webcasting in, hopefully you'll be able to hear about some of these technical issues. For those of you who are in attendance, when we break from this panel, they'll be available as you go back to your displays. They'll break up and visit each one of your displays. So if you have questions or interests or any kind of information you'd like to glean from them, they'll be available to talk to you. So why don't we start? Let's see. We'll go with, let me just introduce each one individually. Jeremy, well, let me start with Pradeep, who's a graduate research student at the University of Michigan, and he's particularly interested in machine learning and probabilistic inferencing. We have Rich Fredrickson, who's to his left. Rich has his actually doctorate from aerospace engineering. A note on this. One of the things about engineers, if you're an engineer, I'm actually a naval architect by training. Rich is an aerospace engineer. The interesting about engineering is a good engineering degree can take you anywhere you want to go. You may practice one discipline, but a good engineering degree is going to provide you the tools of how to model, how to do the mathematics, so that you can go on any discipline. You're not going to be, if sooner or later you say, oh, I don't want to be a roboticist anymore, chances are you're going to have an opportunity to choose another profession very easily. So that's the beauty about being an engineer. You're not stuck in one field the rest of your life. You get to do many different things, and it's exciting. So Rich is an aerospace engineer from the University of Michigan. We have, let me see, Dan Bartz from Booz Allen and Hamilton, and Dan has his Bachelor of Science in Mechanical and Electrical Engineer from Kettering, and Dan has actually worked on the Oshkosh's 2007 Urban Challenge team, and he's done a lot of work in automotive active safety and vehicle sensors. Jeremy, I don't know if I didn't introduce you yet. He's from our U.S. Army TARDEC, and he's actually a graduate student currently. Is that right, Jeremy?
That's correct.
Yep, from studying mechatronic systems and engineering program at Lawrence Tech. And some of his interests are in modeling and optimization of fuel economy, mobility of multi-wheel drive vehicles, intuitive manipulation control, etc. And then Mark Salamango from 6 Zulu has had a great career working on various aspects of software for handheld devices, for sensors, for vehicle diagnostics, and the like. So each one of them, interestingly enough, we've got from different universities from this state and different disciplines that they've practiced. And what I'd like to do is just start from the end and work towards me and give us 5 minutes, 10 minutes of one answering the questions of what's interesting in robotics, what technical issues that have you found interesting, and where do you think it's going in the future? Okay, go, Phil.
All right. Well, I think it sounded like Andy kind of skipped me there, but my name's Phil Mooney. I'm actually a software engineer for Quantum Signal. It's an engineering company. We do a lot of stuff. Mostly, I mean, it's all engineering based, but a lot of our contracts are government based, doing image processing, robotics, anything in that field. We really kind of dig in and just enjoy doing. I've also been a part of the IGBC for Lawrence Tech when I was there as a graduate student. I don't know if anyone's familiar with what that is, but basically it's a competition for collegiates where they get to kind of build their own robot and take it out and compete in two competitions, one for autonomous and one for navigation. It's really a great experience for kids, and just getting experience for potential jobs and just for fun. So wherever you guys head off to, definitely check and see, if they do anything in the IGBC competition. Now it looks like there's a large number of people who perhaps are professionals in this field. I want to warn you that I am going to intentionally ignore you. Really, I just want to focus my speech on the kids, kind of get them excited about it. Let's see. I will try my best to answer the questions that Andy kind of asked of us. But really, I'll go kind of in a broad, my opinions, my thoughts, things I've learned. And I welcome you guys to just come up to me. I think I'm pretty sociable. Come up, ask me any questions afterward, and we can go in more in depth on anything. So what do I find robotics exciting? For me, it's the challenge. The biggest thing is it's a very complex. There's a lot of complex problems that are being asked, and they're challenging, and that's difficult, and that's fun. Nobody necessarily likes something simple. But complex stuff is a lot more exciting, at least for me personally. Oftentimes, too, these are first generation kind of questions and solutions. So potentially things that people haven't asked before, or people don't have answers for. That's not always the case. A lot of times you get the opportunity to build upon what someone else has kind of laid the path for, which can still be exciting because you get to make it more efficient, kind of try and bring your own thoughts to it. Really, they've asked me to talk about sensors, and I'll try and focus more specifically on that. I think for sensors, generally, I don't know if anyone finds sensors exciting, but they're very helpful. When you're involved with, making algorithms or trying to make decisions, I think some of the most important things you can have is information. I mean, the more information you can have, the more decisions you can make, the more complex decisions you can make. So sensors are huge as far as, getting more information so you can make better decisions. Now, if I was presented with a problem that had to do with sensors, I think there's a few steps that I would take, and I would welcome you guys to take similar steps, or obviously you can vary. But things that I found to be very useful when dealing with sensors and trying to tackle a problem is, first of all, reading the documentation. Now that might not be the most exciting reading you've ever had, trying to read about hardware, but typically I've found that these companies that make the hardware do a pretty good job of documenting the capabilities, the functionality, and what they provide. So start from there. Just try and work your way through it. And once you get to that point, you can start implementing or start thinking about it. Once you know the functionality that it has. I think some of the big things for me that I find when using sensors, and specifically when these sensors get put into bigger platforms and things start being all fused together, is trying to create test applications for each sensor you have. I've seen so many times, and specifically for me as well, where things go wrong on this platform and you're not quite sure what went wrong, and you're trying to figure it out. One of the easiest ways to start going through and figuring out exactly, pinpoint what happened, is to have some simple test case, some simple temp applications for these sensors. And that way you can say, okay, is it the LiDAR? Why is the LiDAR not working? You can run this simple application. It doesn't have to be anything fancy, just something that tests whether it's working or not. Start from there, and then you can start to eliminate certain things, and really that helps you hone in on what the problem is. Debugging is a huge issue when doing any kind of software, not just robotics. Also, I would highly recommend doing some kind of fake or simulated data. Oftentimes, specifically in this state, we don't necessarily always have the capability to run our robots out in the snow. Sometimes they're shelved for long periods of time because of weather. If you can get some kind of simulated data, fake data, recorded data from the real sensor and kind of play that back, you can therefore continue to work on certain aspects of whatever your problem is towards whatever solution you may have. It's not only just weather conditions, also, at least in college, in my experiences, even in professionally, You know, everyone wants the robot's attention. The hardware people may need to work on the robot, meaning the software people can't be testing things and running their algorithms. The software people may need it to go do something, and some other software person who's trying to do something else never gets to work on it. So there's this constant fight for time with robots that I found, and getting some kind of simulated fake data is extremely important. That way people can continue to do their things, and once they have their scheduled time to work with the robot, then they can go ahead and they can go ahead and try it on the real thing. And there should be that easy transition between both. It's not ideal, but for testing purposes, for trying to find solutions, I think it'll work out pretty good. And really, I have some general tips, not necessarily guided towards sensors, but just things that I've seen specifically in competition, specifically in robots, is what I would say to start small and build up from there. There's a lot of people who have great ideas and they're very complex, which is what we're looking for. I mean, these are complex problems, we're looking for complex solutions. However, you can't just start there. You have to start small. I mean, I can't stress how important that is. I've seen so many times on my own team, I've even got myself into doing this, and I've seen other teams fail because of this. They have this large, complex thought, they just dive into it, and at the end of the day, time runs out, they don't have nothing. One, because they couldn't figure out why their complex thing didn't work. They don't understand their complex thing. Or they just ran out of time because it was too complex. People who don't generally have a lot of experience in making large-scale products don't have an understanding of how long it really takes and what to account for in that estimation. I think we struggle with that every day, even as a professional. It's hard to estimate how long is this going to take. You don't always see all the things that could potentially go wrong. So start small. You can always build up from small, and from small you at least have something you can be proud of, something you can use. If it's complex, it never works. That'll be very disappointing in the end. So start small, start building up, and you may never reach that complex thing that you would chat for, and you'll understand maybe later down the road why. But at least you had something to go off of, something to try, something to be proud of, and maybe people down the line can build off whatever you had. And I guess the last thing, as far as general tips, would be teamwork. I know I'm sure every teacher, every person, as I've told you, to work together, and teamwork's important, but it really is. I know, at least in my field, software developers tend to be very individualized. They want to do everything themselves, and it's good to force us to work together as people to get more ideas flowing. It's even if you have a great idea and it may be perfect, it's not a bad idea to shoot it off someone else and say, hey, can you see any flaws with this? Play devil's advocate with it. Those sort of things. So hopefully that's a general those are things that I've learned, experiences that I've had, and hopefully that will help you guys a little bit. As far as I know I'm kind of running long on time here, so where robots are in the future, I'm sure everyone else will answer that. Obviously there's a significant amount of potential there, and we're really hoping that you guys come aboard and help us with these problems, because we really could use your help.
Great. Jeremy, can you talk a little bit about platforms?
Sure. With platforms, I'm going to try not to get into too much of the military side of it, just more so generalized. Platforms, in my opinion, are often neglected. Even I worked with him on IGVC. We were teammates, and I would, sit there, work on get this cool idea. I go with the team, hey, look at this. I'm gonna do this for the platform. I was the hardware guy, and he's like, I don't care as long as it moves. So, that's good. We all have our different, pieces, but if it doesn't move, it's not a robot. So you have to, you can't neglect. That's the good thing about robotics. You can't neglect anything. Every little piece is a piece of the puzzle. So if you forget one thing, it's going to be short. You can, with a platform, especially to get into the military, everything's going towards interoperability. So you're going to have a chassis, a system, and you're going to have one type of, or three types, whatever, of sensors on it, and you might need to change them. And instead of being able just to grab anything off the shelf, and plug it in, you need to be able to do that. And the problem is currently you can't. So as far as designing, you need to think in those terms. How else could this be used? With the platform, you're going to get, the platform is the power source. It is its mobility. It is the kind of the beating heart. Everything else, obviously, software is very large, and that is a key point. But they all have to work together. So, from what I've seen, there's been a lot of neglect, a lot of neglect in that. You have to select your proper power system. You know, is it fuel? Is it an engine? Is it electric? If it's electric, what kind of batteries is it? Is it lithium ion? Is it NiCad? There's a lot of different things you have to go through, and then from there you have to get into, well, what kind of motors do I use? What kind of control algorithms? What kind of overall motor control and whatnot? And then you have to, how do I interface? How do I supply power to these different aspects? Is there any intelligence on board? Do these communicate back and forth? So not only if you're one of an engineer, electrical, mechanical, maybe even software that is working on a platform, you have to also know what else is going on. I had to go talk to him and say, okay, well, what kind of camera are you putting on? How do I interface with this? How do I give you power? What do you need? And often or not, early on in your engineering cycle, they might not know. But so you have to try to, go forth without, and try to, help incorporate everything in there still. What are the three things?
Where do you see it going in the future?
In the future, especially for military, they're going to have tons of aspects because their prime purpose is risk mitigation. In industry, it's to develop repetitive tasks. So there's a lot of movies out there, iRobot, a bunch of other things that you I don't want to be throwing that out there, but there is this future that's very unknown. I couldn't tell you where it's going, but it's definitely, robotics is going to be a major part of everybody's life. And being able to understand it, being able to contribute towards it, I think that just is where you want to be.
So the next speaker is one of Professor Olson's graduate research students, and Pradeep got to spend 5 weeks in Australia. So, but when you talk to him, if you talk to him today, don't ask him about Australia. Talk to him about robotics. But Pradeep, can you talk a little bit about perception and what some of the technical issues you find interesting in regards to that?
Hey, I'm Pradeep. So I wanted to, when I'll be speaking, I'll ask a few questions to the students here, just to gauge whether you understand some of the terms that I'll be using. So I'll be talking about perception. Do you guys understand what perception is? I mean, can we do a show of hands? Okay. Do you want to define perception?
Would it be like your eyesight, any kind of that you're getting back from your surroundings?
Yes. That's a very specific example, but it's still right. A very short and very descriptive way of telling you what perception is that it's the science of making the robot understand its surroundings. So that's what perception is. It just need not be done using a camera. It can be done using any sensor, maybe like a sonar or radar. It's just the science of making the robot understand its surroundings. So the first question I've been asked to speak about is like, why is this field a hard field? So one of the main things that makes this a hard field is that there are a lot of fields that have hard problems in them, but this is one particular field that people have been trying to solve problems right from 1960s probably, and there's no satisfactory solution for these problems. People have been trying to recognize objects right from the 1960s, and still even today we are not at a very good level at recognizing objects. So that's what makes perception a very hard field, and that's what makes it exciting too. When you have hard problems and you want to find solutions to them, that's what makes the field and problems exciting. Now, solving such problems in perception means that you can vastly change how robots interact with the environment. For example, a robot in this room, when it sees all these chairs here, it's going to think of them as obstacles. But we as humans, if we see a chair, we would just move the chair and proceed past the chair. So the robot is like very limited in its understanding of the environment, and that's what we want. We are trying to improve in the field of perception. That is like we want the robot to understand the semantics of the environment too. That the chair can be moved. It's not just a bunch of points in space. So the next thing I've been asked to talk about is technical issues in this field. So one particular thing that you would notice, for example, is that suppose I see this monitor here and I switch off the lights and I see this monitor, I would still recognize this as a monitor. Currently, this is a very hard problem. I mean, we humans can do this very easily. We have so much bottom-up and top-down information that we have information that there was a monitor here prior to the lights being switched off, and we can combine all that information to recognize that the monitor was here. But doing such things for a robot needs a lot of we need to develop a lot of new methods to help robots do such kind of stuff. I've also been asked to talk about what are the new sorts of methods that people do to solve such problems. What are the new methods that people use to solve such problems? How many of you understand what probability is? I mean, have you taken a course in probability, or do you just know?
I
So,
just know what probability is. It's the chance of an outcome type of thing.
sure. So people now have, I mean, if you followed Professor Olson's talk, there was a very nice example of how probability could solve a problem. I don't know your name, but I recognize you by your face. You actually asked a question to Professor Olson that what do you do when there is contradicting information for the positions of two robots? Now you can't solve that without by having one solution for each of those robots. But when you do it in a probabilistic sense, by assigning certain uncertainties to each robot, you can solve this problem. So these are the kind of methods that people have adopted to solve problems in this field. So which means that in future that I would encourage you to study subjects like probability and math. One thing that I've learned from experience is that to actually understand engineering, you need to work with engineers and try to follow their methods. But to innovate in engineering, you would need a solid understanding of the math and science behind them. So in this young age, it's nice to get a good understanding of the math and science behind the engineering. And when you come to college, you will find that you can innovate in engineering rather than just following what others tell you. Finally, I'll conclude by telling you what I think the future of perception is. I'm just a second-year PhD student, so my my view of the future is pretty limited. So I'll tell you what.
Doesn't get any better.
So robots in the near future will try to assist humans in certain specific tasks. For example, they might help with recognizing humans in a certain scene, or recognizing cars in a certain scene to facilitate some actions. But there is also this question of trust versus ability. The robot might be able to do something, but are you willing to trust the robot to do that? For example, I'm okay with a robot serving me dinner, but I really like my dog, and I don't want a robot taking care of my dog. So there are some moral issues there. But in the near future, we can expect that robots will do small, well-defined tasks for us.
Thank you. Next speaker will be Rich Fredrickson, and he's going to be talking about intelligence for autonomy.
Okay, well, so I work for SOAR Technology, and we essentially have a platform, a rule-based platform for like high-level autonomy, even possibly, I guess, higher than what Ed was talking about before, where he had a very specific task that he wanted to essentially accomplish in a kind of an optimized way. We've got maybe a different focus, which is we'd like to do a lot of tasks in, say, for the military in a doctrinally correct way. So we have our rule system. We might interview actual human experts about how they do a task, like say a Marine resupply mission, when they hand off or check in with someone else in at the forward operating base that they're getting to. Why they might check in one way, why they might check in another way. So we do a lot of interviews with subject matter experts and try to break down their reasoning process into these really kind of small, essentially if-then rules that that for a large system you may have, I don't know, 20 to 30,000 of these rules that create what we call a problem space, where you essentially take the agent's memory and view of the world, and you try to answer a specific problem in that problem space. Like, should I contact someone to tell them that I'm almost reaching my destination? So we do that, and that's quite interesting. Probably the most interesting part about that is you get to talk to a lot of interesting people. So we've done intelligent agents that mimic how Air Force fighter pilots fly their missions, and how they might do close air support missions. And those guys are always a blast to talk to. They are always full of great stories, and especially Marines too. They're full of great stories also, but they're kind of R-rated, and now we can't talk about that. So, so that's I think a particularly interesting thing for the way we approach stuff that you won't probably find with other people on the panel. So we get to actually talk to humans and try to dissect how they do their problem, or how they solve a particular problem. Let's see. I mean, in general, for general problem solving, I think what is it? The KISS idea, keep it simple, stupid, is very appropriate. Always try to start out with something simple and build on that. I've also seen, as a fellow panelist down there commented, a lot of projects that have high hopes and are very complicated, and they just kind of never get to that point where they function. It might be a complicated system with 10 components, and each component kind of almost works well. Maybe it works 80% of the time. But if you put 10 components together that work 80% of the time, you get something that rarely works. So, I've seen that more than once. So I'd say that's a very good and general way to approach problem solving. Also, it usually never hurts to get specific, at least for a while, especially if you're floundering with you kind of set your goal too high. Maybe you want to create a system that picks up balls, but you can't pick up every ball. Let's just get it to work with this ball, essentially. That's a very, very useful approach. Let's see, what were some of the other things?
Where do you think it's going?
Where do I think it's going? I don't know. I liked some of the panelists this morning. The way they seem to describe a realistic future where robotics will kind of seep into various areas that we already have tools for. Like cars will get to be more and more like robots, essentially. I think that's a very realistic view of the future. I'm not really expecting, C-3PO anytime soon or anything like that. I think that's still a long ways off.
So a man in a costume isn't?
Actually, I would expect that.
Okay.
But yeah, so I think, someday, maybe when you guys are older, you'll be helping my generation, decide which robot to get. A lot like my generation helps our parents, try to figure out what computer they should buy or how to install an antivirus for the umpteenth time on their machine or clean it off. So, any other questions?
No, that's good. Mark, you talk a little bit about comms, software architecture, or something?
Sure. Yeah, I actually have a 47-slide statistical analysis presentation. I don't know if there's someone that can pull it up. I'm serious.
Oh,
yeah, there's a slide in there.
Okay.
Can we get that up?
Where's
Is there
Phil?
someone?
Phil's
It's
Phil.
pretty critical to my talk here.
He's
I
coming.
I
He's coming.
spent all that time on
I'll tell you what.
47 slides, and then statistics is not my strong point either. As I start, I have to add one thing to what Jeff was saying earlier. I really like your little mantra about, you know, doing cool things until you die. I think the only thing that I would add to that is that make sure you're having fun while you're doing them. I think pretty much everyone that's ever worked, yeah, I'm not Corey, I'm the handsome one. I think pretty much anyone that's worked with me realizes that I try to have fun in pretty much anything I do, even talking amongst you with the panel. So if we start at the top at the beginning of Candyland here, the character you see in the upper left corner is what I would look like if I were a superhero rock star, which, psst, don't tell anyone. And as we kind of walk around the communication map here and try to stay out of Gumdrop Bog or whatever it's called, you see, you know, communication started long time ago, right? We had, you know, the caveman poking another guy to have him draw on the wall, as the comic says. So we started, you know, at cave drawings and stuff like that. We kind of moved over to smoke signals, and then if you kind of look at the next one, you can see, you know, the kid's talking to his younger brother saying, gosh, you know, Wi-Fi used to be spotty out here. It's great that we have this technology now. And as we kind of go through, you can see that there's been a whole bunch of communication technologies over the last few years. And actually, within the last 10 years, lots of stuff has happened. I mean, you have Bluetooth, you have Wi-Fi, Zigbee, you have the 3G networks, the 4G networks, all kinds of things keep kind of coming up. And I think there's more and more coming. You know, the kind of the Moore's law of communication is just getting started. So, so the things that are really interesting to me, though, now that we have this kind of framework or some of these base technologies, is picking and choosing which ones to use in certain situations, right? So in some situations, and cell phones are starting to do this now. Some situations, a comm may be better because it's faster speeds, right? So when I'm at home, it's really great that I have my Wi-Fi connection, right? I can, you know, my computer works really fast. But when I step outside my home, I have my cell phone network, which isn't quite as fast, right? Also, when I step in the car and I got Bluetooth kicking, that's pretty cool. So the idea is, you know, change based on power constraints, change based on bandwidth, change based on, you know, location, things like that, I think are very interesting, and they're starting to kind of come along. Now, I wasn't going to talk about this per se, but Ed Olson kind of got me thinking that this project that I did a few years ago when I worked for the Army was very similar to the Magic competition. And for 5 or 6 years, I worked for the U.S. Army, and I managed a laboratory called the Pervasive Computing Lab. And pervasive computing is all about sensors all over talking to each other through comms channels and, you know, sharing sensor data and stuff like that. So we were asked, our lab was asked to do security for the Super Bowl that was here in Detroit. And so where we were very similar to what Ed was doing, we were doing Magic but with people. So we didn't have the added task of having to build a robot that had wheels and stuff. We outfitted the people with sensors, and we had them walking around and basically mapping out the area, looking for chemical, biological, nuclear, radiological, all these other kinds of different threats. And so we were mapping this stuff out on these handheld embedded devices, and we were able to share that information through something called an ad hoc mesh network, so that each participant, each robot, human robot, in this situation knew exactly what everyone else was seeing, and we also had a command station that could see what everyone else was seeing as well, so that they could deploy people into certain areas. We did a similar thing for several NASCAR events, which gets me kind of to the point of some issues you run into with comms. Now, if you've never been to a NASCAR event, for the people watching alone, you gotta try it out. You can do that. You can go to Walmart real late at night. There's lots of different parallels, but one of the things that we noticed as it slowly penetrates the crowd, one of the things that we noticed is when you go to these NASCAR events or you go to the Super Bowl, one thing that you see is there are billions of people with networks, comms networks out there. And it turns out when you have 1,802.11 connections all over, nothing really gets through. If you've ever gone to a University of Michigan game, you'll find that your cell phone doesn't work all that well, right? I happen to actually go to school there, so I had to get my U of M plug-in too, which is another reason I really liked Ed's presentation. But I digress. So yeah, you go to these different things and you see that there's a million different comms channels being used, and it's really nice when you have something that can switch from one to another really quickly. So that's another thing to think about when you're doing comms. And along those lines, test, test, test. I mean, you can't do enough testing. We, as we were getting ready for the Super Bowl, we had, I don't know, 20 different Wi-Fi routers set up in our lab just to see what it would be like. And it turns out the way that we overcame that obstacle was that we had the craziest amplifiers by one of our suppliers that we just outpowered everyone. I mean, ESPN was like, why the hell can't we get a signal? Like, what are these breadcrumb things I'm seeing on our network? So anyway, yeah, testing is very critical. And that's kind of how I see us progressing here is I see cars talking to each other. You know, the car a mile ahead of us just had a traction control issue. Well, why can't we use that sensor data, send that information over the network to let other vehicles know? Let other vehicles, you know, within a certain radius, share information about, you know, weather, road conditions, things like that. So in the future, that's what I see. I see these comms channels turning on and off based on a rules list. I worked with IBM on setting up a lot of that stuff years ago, and it's technology that's starting to kind of come along into the mainstream. So that's kind of my crystal ball.
Great. Dan, can you talk about user interfaces for us?
Okay. User interfaces. Maybe a little background about
Or
me.
whatever you want to talk
Okay.
about.
I did my master's at Carnegie Mellon, worked on 2 of the DARPA challenges, which is a lot of fun. I worked a lot in automotive, and now I work with Dr. Overhaul at Tardec doing kind of technology strategy and looking at what's all the technology going on in the world, and there's a lot of really cool stuff going on out there. And one of the things I noticed was a lot of the really good selling products tend to have really good user interfaces, like real novel interfaces, real simpler user interfaces, but you look at like the iPhone and what they did with multi-touch, what we did with gesture-based controls. You look at now with the Xbox Kinect, where you are your own controller. You don't have to have a separate controller, or something like the iRobot Roomba, where it's a robot you don't have to program. You just set it up and it cleans your living room. These are some really innovative products, and there's some interesting design elements that go into designing a user interface. And there's a concept called universal design, which is, if you want to design a product that's attractive to everybody, you want to make it sure that anyone can use it. So like my mom can figure out how to use, the new VCR or DVD player, Blu-ray player, whatever you want to call it. I had a program on VCR when I was a kid. It has to be flexible, so it may not be used for what you originally designed it for, but it still should be useful. It needs to be intuitive, so you don't have to read the manual. Any good product, you shouldn't have to pick up a manual. Tolerant of error, meaning that that the person may make a mistake, and you should try to accommodate those mistakes and help them fix their mistakes without making it a big deal. Like the good undo button in most of our Office applications is an example of tolerating mistakes. Should be provide information that's easy to understand. So, instead of having just the check engine light, you actually know what you're supposed to do. Like I had a check engine light because my gas cap wasn't tightened down, and I had to take it to the dealership. They said, "Oh yeah, you should tighten down your gas cap." Well, that's not providing information in an easy to understand method. I could have tightened the gas cap myself if I had gotten that information. And you have to make things that are reasonably sized and designed well. Albert Einstein once said, "Make things as simple as possible, but not simpler." And simple sounds really easy, but it turns out to do a lot of these really innovative products, it's a lot harder than you think. If you think about the Xbox Kinect sensor, it's a 3-dimensional webcam that can see people, but it took millions of dollars of development to develop that system. If you look at some of the robots we use in industry, 6 manipulated arms, there's a lot of matrix math that goes in that. Has anyone here done 6 degree of freedom inverse kinematics? You know what I'm talking about, right?
Yeah, everybody sign up.
So it was a very complicated math problem to take something that would have been hard to use and make it a lot simpler. So just because something is simple to use and has a simple user interface doesn't mean that it's really easy to program. It means that you have to really think about the problem a lot, think about who you want to use your product, and then go out of the way to make it as simple as possible. Like, you know, Einstein says, you know, keep on driving it to be simpler and simpler and simpler until there's no simpler you can make it and still be able to do the task. And this strives to a lot of stuff, you know, some of these other guys talked about before, is you have to have, you know, more sensors, you have to have more intelligence, you know, and we're seeing a lot of this stuff with some of the automotive active safety things where, like, traction control is a user interface thing. It makes the car drive more consistent with the way you want to drive it. You don't have to think about, you know, do I have to take my foot off the gas or do I have to put the brake, you know, on at this point? So they're using a lot of these sensors and this intelligence to help make the user interface more intuitive and simpler. And, you know, I've got a kind of a list of some of the stuff I've been tracking in terms of future user interfaces or technologies where we're going to get to where we're going. Obviously, we've seen like the multi-touch on the iPads and the iPhones. I think we're going to see some of the old buttons come back, but with multi-touch on top buttons. And some of the one of the PlayStation controllers has buttons that are touch sensitive, so you can use it as a mouse or you can use it as a keyboard. We've seen cars where as you put your finger over the button, you can see on your windshield on the heads-up display which button your finger is touching, so that you know you're pushing the right button without having to take your eyes off the road. You know, there's a lot of speech applications. You know, talking cars have come back. If you remember the 80s where they had talking cars, they're back. But the speech recognition is not perfect yet. So there's a lot of companies working on adding lip reading to speech recognition, which could be something to help people who are, you know, with people with different disabilities. And you look at some of the stuff with driver or user monitoring, right? There are some cars now that can actually watch the driver, figure out if he's paying attention, and if he's not paying attention and maybe is about to get in a crash, you can warn them. But if he is paying attention, they assume that he knows, you know, a little bit more about what he's looking at. So systems that are able to actually understand the user and what their capabilities are, and whether they're paying attention or not, and make you know, react based on that that knowledge. And we're seeing some really cool stuff in displays. Has anyone seen the new Nintendo 3DS? The DSi with the 3D display. You know, the new PlayStation you can plug into a 3D TV. We're going to see some really cool 3D displays coming out. Some that are called volumetric displays, which are not just like to the left and the right. It's actually something that looks, you know, physically real. We're seeing rewritable holograms is a new technology. And one thing that's kind of cool coming out of Japan in the camera market is instead of having a display in the back of your camera, they have the head-mounted goggle like some of the fighter jet pilots have, or I guess the helicopter pilots have, for photographers, so that they can see the picture right on their eye without having to take their head off of what they're looking at. So they can see what their camera's seeing on this little monocle, and it's no longer military technology. It's now technology for, you know, everyday people to use. And we're also seeing really cool stuff happen in the cell phone market with like smartphones, like augmented reality displays where you can hold your camera up at a building and can tell you the name of the building, or you could, if you're in China and you point it at a street sign, it translates it into English from Chinese. And you know, doing these things in such a way that it makes the user's life easier, so that he can, you know, do his main task. And you know, we look at you know, there's a lot of issues with that in the military applications, but in the civilian applications, it's how can you make a car easier to drive so you can focus on doing the driving and not have to focus on all these other things that are involved in the car, like the distractions that Dr. Everhart was talking about earlier. So those are some of the types of things I've been seeing in user interfaces. And I think the right type of user interface is not just doing one thing because everyone's doing it. You know, everyone got really big on touch because the iPad had touch. But touch doesn't work, you know, in all circumstances. I don't think some of the touch interfaces on cars work all that great because I can't tell what button I'm pushing if I can't, you know, feel it. So, so like I said, you know, back to the universal design, you know, making things that everyone can use, that's flexible, easy to understand, tolerant of error, and, you know, provides you useful information. I think if you stick to those rules and you know, work really hard to understand the person who's going to be using the system, I think you know, you can do a pretty good job. So.
Great, thank you. I want to ask, does anybody have any questions they'd like to ask some of those panelists?
Just a quick question. How many of you are familiar with FIRST, or have any of you been active with FIRST Robotics? Right? Okay.
And we're going to, after this panel, John's going to come up and talk a little bit about FIRST too for us. Yeah. You know, Jim.
So, I heard all you guys talk. Do you feel, not your graduate work, because all of you guys obviously have some level of graduate, did your undergrad prepare you for the job you're in? I'm kind of curious. I mean, the question goes toward education, maybe even back to high school. Maybe it's a loaded question. Are we teaching the right things to engineering students to prepare them for this new environment?
I would personally say no, and that's disappointing. I think obviously it appears that, you know, high school and specifically undergrad are more focused on fundamentals and kind of building you up from there, which I think is extremely important. But I personally never even got involved in robotics or knew much about it until my graduate course at Lawrence Tech. I took an AI course and it was a big disappointment in undergraduate. Just very basic, not really like, there's cool things that people are doing with it, kind of like today, where you're like, this is what they're doing with it. It was just very basic kind of understanding of artificial intelligence, not really useful applications for it. So I personally would say no, but it'd be awesome if, you know, I think obviously the first is you know, bringing upon that awareness, which I never had. So it's good to see. But for me personally, no, I didn't have that upbringing.
Well, let's just keep going down the line.
I would have to say no as well. I mean, in my graduate studies, they have been a lot more, and actually helping me with my career. Undergraduate, I mean, I came out struggling in some areas. A lot of it is what you make of it. You know, there's partying. So,
Not in Michigan. Not in Michigan, right?
That can prepare you for life.
I did 6 years in the Marine Corps as a reserve through school, so my attention span was even a little bit less. But all in all, I mean, the information's out there. Is the curriculum really helping you? Yes and no. I mean, it builds you a foundation, but trying to take that foundation and apply it is the challenge. In some areas, you know, they do okay. In other areas, there is a lack. I think they need to be not so much single set. I mean, you know, I started out as an electrical engineer, and now I do more mechanical than anything. And yes, that's good, but now going back, if I had designed a circuit, I'd have to start pulling out some books. So, I mean, not that I can't do it, but it's just, you know, everyday practice. So, yes, there needs to be a little bit more, but also spend a little more time studying, less time partying.
So I didn't do my undergraduate education here in the US. I did my undergraduate in India. So what I say might not directly apply to people, but I can just give a comparison. So compared to the facilities that the universities here have, well, India has like very few facilities, but of course we were taught the right fundamentals and stuff. But I think what made the difference is the kind of people that I got to interact with during my undergraduate education. So I think even if undergraduate education doesn't really get you interested in something, or you only learn very little of something, it sets you up with the right kind of people who also want to do engineering, who are also interested in creating new things, and it sort of changes your outlook to life. So that's what made the difference.
Yeah, I'd say, yeah, the specific things you learn probably aren't that important. I mean, the things that you learn that are important are like, how do you conduct an experiment to find out what thing is broken in your system, right? That kind of logical approach to taking apart a system, changing one thing, seeing if it breaks what you think it should break, you know, that kind of thinking. That does translate from undergrad to real life. But a lot of the specific technologies that we work with every day really didn't exist when we were in school. So I find it's a constant, you're constantly learning new things. I mean, I feel like I study harder not being in school than when I was in school. So.
Yeah, my take on the thing is that my undergrad at University of Michigan was great, a really great foundation, but I didn't really start learning things until I started building things on my own. Once I started working, that's when I learned. I mean, you learn what breaks, you learn what works, you learn how to work with people better. I mean, I don't know how many of you have been in a collaborative environment where your professor or your teacher said, you, and you have to work together to build this. And you go, oh, I gotta work with the smelly kid. I gotta work with the girl that doesn't want to do this. I gotta work with the guy that's this guy. You know, and it's like, and you can't relate to anyone, and it doesn't really. Yeah, I'm tracking. I was there too. So I spent, I did my foundational undergrad stuff. Then I went into the commercial world for a while, built a lot of stuff. Then I went back to grad school, and grad school was, by then it was like so easy because I had already built a lot of stuff, and here you're hearing theories and stuff like that, and you're like, okay, now I know how to apply that theory to this specific thing that I've done in the past or that I'm working on now. So yeah, I think trying to find the balance where you're actually building stuff when you're in undergrad or in high school or whatever. That's why I think FIRST is great. I think IGVC is a good step. I think there's a lot of different things that to engage people in actually building stuff. Plus, you get to kick it. You say, I built this. You learn all the principles. There's a big thrust in education right now where it's not just I'm learning math or I'm learning science or I'm learning this or that. You're learning all these things on one project. So that's really cool when you have a project and you say, okay, I need to learn the history of this. I got to write about it. I got to put together a business plan. I got to do some math stuff. I got to do some science stuff. And you're kind of using all the different verticals of education. So.
One thing I found is, I did my undergrad in mechanical and electrical engineering, and you can never learn enough software. That was one thing I think that was a little bit lacking in my undergrad was they had 2 classes for softwares, Pascal and Fortran. Both were completely obsolete by the time I was taking them, so I tested out and I didn't take either one. I really wish they had done Simulink or MATLAB or C++ or Java or any of the more modern languages, because it doesn't matter what field of engineering you go into, software is becoming more and more part of every discipline. And I think my high school education, I'd actually learned a lot more about programming, which made life a lot better when I went into co-op, which is I think where I really learned a lot of stuff. Was I went to school where you co-opt half the year. You went to work at, in my case, I worked at ABB Robotics for a few years, and then GM Research. And that was where I learned the real lessons of engineering, which is if you're designing an assembly line and you screw up on one thing, you're going to get a call and be yelled at, and you have to go out and figure out what the problem is. And when you're releasing things into the real world, you've got to make sure everything is done right. And you've got to do it on time and on budget, and those are the types of things that you don't really learn as much in the classroom. The other thing I did learn a lot from my undergrad, which is Kettering University, was you've got to go out and meet people. You got to go when speakers are coming in and network and find all the people in the future who you're going to be working with, because it turns out the world is a lot smaller place than you think it is, especially if you start to meet a lot of people. And building your network and just finding out about all the people and all the cool stuff they're doing can be really helpful. That and I think it was Mark had said it was one of the things, you only learn what you do. There's a famous Italian quote where it's like you can only really understand some things that you make. And getting involved in things like FIRST Robotics or any of these other types of projects where you get to build stuff, you're going to learn a lot more than having a textbook on it or having a professor talk about it. The real way to learn is to go out and do stuff. And if you're not happy with the classes you're having in school, you got to find something on your own time, extracurricular activities, to go in to learn some of these new areas. And with my undergrad, robotics was something I kind of did on my own, working on different types of robotic systems or programming systems, and I think I learned a lot from that. So
I'm going to also say something. Ed, correct me if I'm wrong, or if you want to shoot me. As a professor at the University of Michigan, hey, when you go as an undergrad, challenge your professors too. If you don't quite get what they're saying, what they're teaching you or the lesson plan, make sure you go in there and you challenge them and say, why am I learning this? What does it mean? And because it's important. This is your education too. And the I would say the professors like to hear that because they're trying to figure out who my students am I going to want in graduate school. And it's that interest in showing that engagement and also your grades. But just don't sit back and take everything that your professors are throwing at you without challenging it if you don't understand it. So I think it's both ways. It's a two-way street. It's one, the infrastructure, but it's two, as students, be engaged. Yep. Any other questions? Okay, so one of the things, just to wrap up, what I heard today from the panelists, some common themes: simplicity, KISS, keep it simple, stupid is the principle, and it's really on two fronts. It's one, in how you decompose the problem. Don't make it overcomplicated, but two, as you design the system. As you were saying, Dan, I think it was you, Dan. Hey, keep it as simple as possible, but it still has to work. You're not going to be as involved with this with your first teams, but as you go into more platforms and different types of platforms, more complexity in the mission, data is really important. So you're going to be, we heard that a couple of times, how data is always, we're struggling to get the information, and it's really hard at times. Another really important one is testing. I'm sure all of you have done a lot of testing with your platforms, your first platforms and robotics. Rich had made a great point. One of the really key lessons you're going to learn as an undergrad is how to set up a test and how to evaluate. And it's really important that you learn that, because that is so key to success of your platform. And then probably the most important one, and then I'm going to throw it over to John Crumby from Bishop Foley, who's going to talk about first, because this is a direct lesson you guys are learning in spades: teamwork. As engineers, teamwork is everything. And with that, I want first to talk about teamwork. Thank you.